Thank you for watching this demo. We are today with Danny Lloyd. Danny, would you like to introduce yourself, please?
I'm Danny. I've been at Aibuild for just over a year now. I've got experience in additive manufacturing since about 2017. I was in the polymer additive manufacturing team at the Manufacturing Technology Centre in Coventry. I led some large format additive manufacturing work there, converting an old large CNC machine into a hybrid large format polymer printer. And then after that, I spent a couple of years at a automotive startup called Revolve, leading their large format robotic 3D printing work there, printing composite tooling, composite patterns, trim tooling, all that kind of stuff. I've also have experience in wire arc additive manufacturing and powder DED. So nice bit of experience to feed into workflows and working on customer applications, things like that.
Absolutely. Perfect, Danny. So just for our audience today, we thought to use to have a demo from Danny and to look at the software a little bit more in detail that we find that could be very useful for the community. So the floor is yours, Danny. Go ahead. I'm excited to see what you will show us.
Good stuff. Thanks, Michael. Let me just share my screen. So we've got a few different workflows we will jump through today, different kinds of technology applications, different slicing modes, features, all that good stuff. So the way that Aibuild works, it's pretty different from your conventional 3D printing slicer, where you have a list of settings and you press slice, something magical happens in a black box and you get an output that you can't really then do very much with. That's great for desktop kind of FDM printers and finely tuned and quite highly controlled technology at this stage. For large format 3D printing, for DED, for wire arc additive, for concrete 3D printing, that kind of method isn't too suitable. On the other end of the scale, we've got like a CAD CAM type solution. They are absolutely fantastic for CNC, for milling. They're not as finely tuned for additive manufacturing, and they can be quite difficult to use, quite long to create toolpaths, and like I say, they're not really set up for additive manufacturing. Whereas Aibuild sits somewhere in the middle. We have a lot of automation for 3D printing. We slice parts very quickly, very powerfully. And we also have the ability to go in, fine-tune our process, optimize it in numerous different ways that apply to all these kind of technologies that we work with. So it's very powerful in that respect. And Aibuild, we've been robotic 3D printing for the past 10 years. We've got lots of in-house additive manufacturing experience across technologies and materials. So all of that feeds into the software. We can test our own software, get our own experience, and then, of course, all the collective experience of our partners and customers all feeds into the software too. So the way it works is, on the right-hand side, we have an example workflow. We've actually got kind of a couple workflows in tandem here to show you the differences between different things. And we drag and drop, we call these operators. They're like visual programming blocks. We can drag and drop these into the workflow, chain them together to create your toolpaths. So these are our core operators, our most commonly used ones, but you can see we actually have an awful lot really, and these all come together to create something magic. So we create our and select our robot for the workflow for the project. We pick our material, which has got various thermal density, cost properties associated to it. And then we also pick our nozzle, so we can pick different nozzle sizes, different nozzle calibrations, different extrusion rates, so it's all automatic. So with all that said, let's actually jump into the workflow. The first operator is a load operator, and this will import your CAD or your mesh into the digital workspace. And we can work with step files, OBJ files, STL files, and DXF files in polyline format. So we have this kind of wall here, or mold. We'll actually reuse this part later. If it's loaded in the orientation that it would be naturally from CAD, but we can use our transform operator just to reposition it. Got an interactive gimbal, we can move it around and rotate it, snap it to the bed, things like that. So we've now repositioned it in a more optimal orientation for slicing, large format printing. And then we can feed that transformed mesh into our slice operator. So here's where you find most of your like classic 3D printing settings. but we also have a lot more in terms of slicing modes as well. So very traditional horizontal printing, which is what we're going to start with, and then we'll go into some of the more advanced ones later. But we can also change our plane of slicing with angular. We can have it change throughout the print with multiplanar, and then we have others where we can use guides. We can slice parts radially. We can revolve around a symmetrical part. We can do non-planar printing, vase, segmented, cladding, and we'll see some of these later. So we can define our layer heights, wall thicknesses, our number of walls, where our bead position is, which is all very important. Infill skins, brims and rafts, etc. And the slice operator will convert your mesh or your CAD into polylines. And we work with the polylines for the rest of the workflow. So you can see here we have all our individual layers. We can turn on a solid bead view to get a sense of how it would look as it's actually printed. So we have our bead thicknesses, layer heights. At the minute, we're in the line type view, so we can see our different line types. We've got our brim, and we have our outer wall. But we can change this to various other views, like printing sequence. So if you're printing multiple parts at once, or parts that have got different stages to it, sequence is incredibly important, and I'll show you an example of that as well. And lots of other views here. We can turn on other important views like our seams, so we can see our starts and stops, our direction of printing, and controlling where these are is also very important because they tend to be an area of material buildup or defects or weaknesses, so positioning these is pretty critical. And we can crop through our individual layers as well. This is about the same level as a one-click slicer at this stage. We slice the part, and then we can feed it into our toolpath where we can assign things like movement speeds, jump settings, deposition control settings, all these types of classic things. We also have safety checks. So for robots, we can look at reach, wrist singularities. We can check workspace limits, axis limits, and we can also look at collision detections. And we'll have a look at a good collision detection workflow a bit later. And the toolpath operator will take all your polyline data and basically turn it into machine data. So we get a lovely kinematic simulation of our print, and we can watch that in real time with the speeds that you provided, or speed it up, drag it back and forth, whatever you want to do. We get some good estimations up here in terms of printing time, material usage. If your material card has got a price associated to it, it'll give you that as well. And then we also get some useful information on what the robot is actually spent doing. So if you have a part that's got lots of travel moves, that can give you useful information to know you can optimize maybe the location of seams, so you're jumping less, things like that. And we get our safety check report, which is good. And then from here, we can download our toolpath. If there's any safety checks that you've not completed, it will prompt you to do so, or you can willfully ignore it if you're brave. And it will download your toolpath file. It will be automatically post-processed in the software to be whatever machine language you need it to be, have any headers and footers you need, any other subroutines, different tokens, etc. So it will be a file that's ready just to upload to your robot or CNC controller and just print.
So this is already the first 4 operators, basically is one slice. So what I see on the right side, you put many different slicing strategies in one workflow.
Yeah, so here what I'm showing is we have also done a thermal simulation on this part. So with the speeds that I've put for this slice, we are going way too fast. And we know that because the material is red across the entire part, and that means it's too hot. So we're printing too quickly. So we can slow that down. So I've just given it different printing speeds here and perform a new thermal simulation. And now it's all green. The first print was about 5-ish hours. The second print, which is now thermally managed, is around 18 hours of printing. So while we get a successful part out, we are dramatically increasing the time that we spend printing. But what I'm showing here is that we can actually put multiple parts in the print bed, whether that's the same part, or you could use another load operator to load a completely different part and slice them. You could give them different slicing settings. And what we're going to do is add more parts, print at the same fast speed as before, so we can thermally manage with more parts and print more for your money, basically. So I mentioned the sequence view before. We've got two parts here. We can see from the color coding where blue is the start and red is the end, that we're printing these parts in series. That's not what we want to do. We can use a simple sort operator to sort them both by layer. And now we'll see from the color coding that they will print in parallel, which is exactly what we want. We can go a step further and we can look at the seams. The seams are here as they were before. When I rotated the other part around, they're in the same relative position, but they're on the opposite side. And that means there's going to be a lot of travel time between the two. But I can reposition our seams. I can update where they are with some coordinates. You can see we have lots of different ways of controlling where our seams are, how they generate. You can do it off features of the geometry, or we can randomize them. But we'll see that by repositioning the seams, they'll be much closer to each other now. So we print one layer of the one on the right and come back on ourselves, and then a small jump here, do the same. So we only have this small jump here now. And our printing time for two parts is going to be around 12-ish hours. So it's roughly double the first part that was way too hot, because we're going at faster speeds, but it's still quicker than the single part.
That's very interesting, because now you leave, because you have a second part, you have time for it to cool down as you move to the second, and ultimately you're saving time by making more parts.
Exactly. You're increasing your throughput, you're increasing your yield, and it's very easy, if you don't have this thermal simulation, to not realize that you're going to print too fast until it's too late. And then you're wasting time, wasting material. Whereas here you can really optimize, load more parts, and find a good combination of settings that will optimize your whole flow. And here the speeds were changed manually, but I'm going to have a look at this example next, where the speeds are changed automatically, and that's very important in this scenario. So here we have some kind of tooling, composite tool, trim tool, whatever it may be. And let's focus on it. We want to slice this part at an angle. If we sliced it the classic horizontal way that we've just done, we'd need loads of infill, loads of skin in order to print this top surface, and it would be a hideous mess. But in large format printing, slicing at an angle, so rather than your planes being this direction, if they're at 45 degrees, this top surface here is actually a 45-degree angle rather than a complete 90-degree shear. And that is an achievable overhang. So all we do for that is we pick our angular slicing mode, and then we define around which plane. So we have our X, Y, Z over here. So we're defining, in this case, 45 degrees around Y. But we can also use things like reference planes, or even have an inbuilt algorithm to determine what is the optimal slicing plane automatically. And all the other settings are the same. So we've got layers, walls, infill, skin, etc.
Yeah, the best plane is very handy. For me as a designer, sometimes I want to make gymnastics around that, especially when it's a design. But it's great to have all options.
Exactly. So now you can see here that we are at a 45-degree angle. We also have our tool rotations view, and these will show your X, Y, Z TCP. So here we have our X, Y, and then Z goes into the nozzle, and that'll be blue. And we can see here, if I just filter out single layer, so it's easier to see, that on every point we have our X, Y, Z TCP, and it's automatically angled it to 45 degrees. So while we have the ability to manually change our tool rotations, for all our slicing modes, it is done automatically based off the information provided. That saves a lot of time. Because this part might be some kind of composite tool, I might want to reposition where my seams are. I may not want them up on this corner here. So we can, say, use different seam settings to reposition them. In this case, I've actually used a combination of operators in the software to extract a polyline that is the same length as the part. So see here, it's the nice exact length that I need it. And then I'm going to move it to this edge here. And then the seams operator, I can use a reference polyline. And this could be a 3D polyline. It can be created in CAD and imported into the software. And that means we can place our guides exactly how we want them across the entire shape of the part. And I've also turned on zipper mode. So while the seams are going to be created along this wall, they're going to be spaced plus or minus 10 millimeters either side. So let's take a look at the results. So you can see we've now got it along this edge, and we can see that the seams are also zippering. So while they're along the same general guide, they're not stacked directly on top of each other. So that can help improve quality.
Yeah.
In the software, we have lots of ability to filter, and that's important because you want to provide, different fixes, optimizations, and improvements, but you want them targeted. So here I'm filtering out our walls. So I'm getting rid of the infill because I don't need to optimize the infill in this scenario. I'm just looking at my two kinds of walls. And then I'm using our optimize operator. So this is a very powerful operator. We can optimize for a number of different things. So we can analyze the curvature, sharp corners of the polylines. We can compare the thickness of the polylines to the CAD file. And we can also look at overhang, or we call it cantilever, because the founders come from a nice architectural background. So that's why they call it cantilever, but it's overhang. And we can, with some parameters, analyze around that data. We can set limits to what we're looking at as well. And based on the analysis, change some feature of the polylines. So here I'm looking at thickness, but we can also say apply a speed multiplier or change our layer heights even. And we can multiply or give it a specific value. So here I'm looking at the corners and I'm going to reduce our extrusion at the maximum curvature. And the reason I'm doing that is because a lot of the time in large format printing, you have natural accelerations, decelerations of the robot or the gantry. So as you approach sharp corners, your robot is going to be cruising at a normal speed, and then it will slow down, and then it will come back out. And your RPM will be, of your extruder, will be at a consistent rate, assuming that it's at a steady speed. And that often means you're over extruding at the corners. This is seen a lot of the time. So what we're doing here is we're actually reducing or applying like a difference in extrusion rates in the corners so that it will even out and give you the exact extrusion that you need. So we can see from the analysis, it's highlighted where all of our corners and turns and curves are. And it will apply this multiplier to the thickness of the polylines. So I can actually go to a thickness view, and we slice the part with a 10 mil wall thickness. So most of the parts are 10 mil, and you can see we have 7.5, so it's been multiplied at these right angle corners here. I could even turn on the solid bead view, and there will be a difference as well. In the real world, the intention is that it all evens out. But
and the pipe is also reflecting the actual thickness, right?
Yeah, exactly. Another quick optimization I'm going to do is combine our walls together. So by default, we have two walls here, and they will be two discrete extrusions. So we'll extrude the outer wall, stop extrusion, move, start extrusion, do the inner wall, and repeat with the infill as well. But it would be neater, quicker, if we didn't stop and start our extrusion in between those points. So what we can do is we can use our make continuous operator. So now you see that our inner walls have gone, but that's because they've actually combined with our outer walls. And now at the location of the seams, we have our walls combined, and the zipper remains. So they've combined together nicely. And we can combine that back with our infill that we filtered out earlier, sort it by layer to make sure it's all printing in the correct order. And then we can feed it into our toolpath operator to print the part. So we can show you how the angle of the tool is all done automatically. So we didn't have to do a thing here. But we'll look at the thermal simulation.
It is important to note here that definitely there are many actions to be done, but at the same time, this is needed after some years of experience making parts. You need to have that kind of flexibility. But for us as well as software developers, we've seen that before we come into full automation, we need to nail every detail. And that's the next step and the next stage of Aibuild, combining these operations to get into full automation. But first, we need to get the basics, get parts out as quickly as possible for our customers, and have the whole gamma of possibilities here for successful prints, but also safeguard us for the investment we put for a future that is fully autonomous.
Exactly. And I suppose it's worth saying that there's a few steps here, but this whole thing probably takes around 10 minutes to put together. And on top of that, because this is all parametric, if I wanted to change some settings of my slice, I don't have to delete all this work here. I can make a change, say, to my wall thickness or number of walls or my infill density, whatever you need to do. And anything connected to that will recalculate as well. So I don't have to delete Control-Z and go back. I can keep making iterative tweaks and see the end result within a matter of seconds. And then, of course,
your intellectual property. Ultimately, what I say to many people, this is your engineering workflow, and we provide the platform for other people to develop their own unique slicer. So every time it can be very unique to what they built, which is very powerful.
And on that kind of idea of individual slicer, the parametric aspect or nature of the software, I could even change the CAD file at the very beginning. And that connected to everything else will recalculate as well. So maybe for your process, your technology, this workflow here is the perfect workflow for printing composite tools at a 45-degree angle. And you need to do 100 of these a year. You don't need to recreate this workflow 100 times.
Yep.
You can just reload the file and it will recalculate and do the whole thing again. Maybe you need to reposition it or move that polyline guide, but that's literally it. You can do that super easy. So it is quicker, incredibly flexible, and powerful. Just to finish this one off, we have our thermal simulation. And because it's at an angle, our start and end layers are much smaller because we're starting and ending at the corners in this kind of boxy geometry. So even though we have a perfect speed for the bulk of our part, it's too fast for the ends. So if we want to automate this, we can do. In the toolpath operator under movement speeds, we can turn on layer time management. And here we have a few automated features to use. The quickest one is this first one here, where we can adapt the speed based on given layer times. And that's what we've done in this example. So for this material, we're provided a minimum and maximum layer time, and the operator will adjust the speed for each individual layer in order to hit this layer time. So that means you're managing your thermal buildup, you're not going too slow and you're not going too quick. Other ways of doing it, the second one, we can provide a minimum and maximum speed, and then it will adjust the speed to thermally optimize it if it's within the window. And then, of course, for metals mainly, we can simply add a pause between layers for a minimum layer time. Not great for polymers. Your material might burn in the extruder, but it's there anyway. And we can see from the second thermal simulation that we have much more green, which is exactly what we want. A couple small outliers, but far better. And that's all related to the material that you pick. It will have material properties associated to it, thermal properties, layer time options, things like that. So this is a real example from one of our customers. This is an automotive part. It's an assembly tool. It's kind of like a rack. And with the standard slice that they started off with, they have a concentric infill, they have outer walls, everything looks normal. We can turn on our solid bead view, And we can see there are a couple gaps. So based on this pattern here, or the concentric pattern, there's gaps. And then because of the differences in radii here, we have gaps here as well. This is what a standard slicer would kind of output, but really they need something that is solid, completely solid. So we're going to optimize this bit by bit. We can filter out different areas, so different boundaries. So we filter out a boundary and we can get the inverse of that filter. Then we can filter by line type. So we can filter filters. So we can keep going until we get the area that we need. And for the infill, we can apply a curvature compensation. For the outer wall, we can apply a curvature compensation. So what this curvature compensation does is it applies this little kink here based off the settings that you provide. So we can see the before and after, So it analyzes where the curves are and it can push them outwards. So that has solved one of those issues by closing off these gaps. But we still need to do more for the infill here. We also applied a curvature compensation for the infill, so it's pushed in a bit further. We can use our optimize operator to analyze for curvature like we did before. So you can see it will highlight all of the different corners of the part, and we can apply thickness multipliers here. But we want to be more targeted than this. Because
what you said now, like in the corner we are seeing on the first move you did, it moved it inwards. But with the optimize, you can bring that back, as you showed before, with the speed to the actual fillet. So still close the gap, but still retain the border.
Yeah. We also have these particular problem areas here, like I showed before. So I want to find a way to get these corners, but without getting the right angles, because these right angles are perfectly fine. I don't want to increase the extrusion here, but we can do that very easily. So I've used a filter to isolate on every layer this particular polyline here. This is the one where we've got these large kinks in. And then I can perform a curvature analysis. So it's analyzing our corners, our curves and turns. And then I can actually filter with that data. So I don't want the right angles, the sharp 90-degree turns. I want these, which are actually less than 90 degrees. So I'm filtering 0 to 89 degrees. And we can see that the output of this, it's taken out our right angles. So the inverse of this filter, of course, all our little right angles. And this is all taken out. And now we can do our thickness optimization here. So I can double the thickness of these particular areas and our polylines with the solid view. We've closed off these gaps now. So they are solid and dense. We've left the right angles perfectly untouched. And we can combine all these things together and see the fruits of our labor. It is now a wonderfully dense component. We can go even further. I showed you the make continuous before that combined those two outer walls, but it's way more powerful than that. At this stage, we can see our seams. So we have one for all the outer walls, one for all the infill, one for all these like boundaries in here. After our make continuous, it's going to make it a single start and stop for every layer. So we can see, and it's still perfectly dense, which is just fantastic. We can also just shift our seams along so that they're not on that tight corner, so we can keep it nice and neat. We can add a brim to make sure that it's nice and solid to the base. And then we can also filter the first layer, slow it down by half, because often the first layer you need to go slower. So we can easily do that. And combine the whole thing together to have our wonderful print. And we can, of course, go ahead and do the toolpath of that. And to make sure that our speeds are all as we want them, there's also a thermal simulation to validate that everything is grand. And I believe it should all be green. Yeah.
Nice.
Let's take a quick look at our mold designer now. So in aerospace, automotive, anywhere that needs mold tooling, the actual design of the tool can take a lot of time. What we can do is take the mold surface or the actual final panel, and we can build a designed for additive mold around that. So we have our surface here. Alternatively, you can load in a step file and select the surfaces that you need to build the tool around. And then rather than slicing the part, we're going to feed it into our mold designer. So we selected our input surface. In our slicing settings, we can define what our different slicing settings are. And we also have staggered layers, and I'll touch on that in a minute. Let us go to a bird's eye view for a second. We can define our extension lengths, which is the bits on the sides here, and the mold depth, which is the distance from the bottom of the surface to the back of the tool. We can add stiffeners. We can define what those stiffeners look like. We can even add air gap. So if it's like an autoclave tool, you need really good airflow around it. We can define what those air gaps look like. We can add forklift pockets, extra walls, all sorts of different things. So let's just cut to the chase and take a look at the output. Yeah. So we can see we have, in a few seconds, gone from a surface to an entire 3D printable tool. We have our nice surface here. We've got our stiffeners, forklift pockets, and then I mentioned staggered layers. If I go to the surface here, we can actually see that the wall behind the front wall is at a different height.
Yeah.
And that is done on purpose with the staggered layers. So you kind of have this bricklaying effect, and it means that when you're milling your outer surface to give it the finish that you need, you are going to minimize the porosity that you would normally get between beads in that gap that you normally get from stacking them side to side on top of each other. So this is something that we did R&D for in-house, and we've finally added it to the software, and it's a really fantastic feature. And it's all done automated, and I believe even, for example, the layer height on the bottom is smaller in order to achieve that effect. So it's all parametric based on the layer heights that you provide. So it could be done manually if you really wanted to. You could filter out layers and change the thickness and all this stuff, but here it's all automatic.
You can also do scanning actions, Danny, to the jumps?
Yes, so in our toolpath operator, under movement speeds, sorry, not under movement speeds, under jumps, we have scanning here. So this is commonly referred to as wiping. So at the end of a polyline, it will wipe on the close of the polyline or on itself if you want to as well. And you can define the speeds and distance that we do that. So that helps close things off, reduce oozing, clean things a lot better. And that could be combined with our deposition controls here. So a lot of our customers will use this deposition before end and actually turn off the extrusion a small distance before the end of a polyline so that they're not over extruding at the end. So a lot of extruders don't come with melt pumps, and there's just natural back pressure in the extruder. And we have got lots of features and settings that we can use to minimize the defects of different kinds of combinations of hardware. So a couple of things we can do to this tool is change our corners. So we've looked at curvature compensation, but here we've got a different use case for it. Because we're all printing with round nozzles, we get rounded edges. And sometimes that means that your milling offsets aren't uniform like you need them to be. So we can filter out the walls that we need here, just the outer wall. And then we can apply a curvature compensation. So here it's quite dramatic, just so we can see it happen. But it will apply this little kink to the toolpath.
Yep.
And that means when it comes to actual printing, you now have enough milling stock in that area. So it'll be milled properly.
Yeah.
We can also make the path continuous. So we've combined our infill reinforcement ribs and outer walls here. We actually already have that setting continuous mode in here, but we can always do it after the fact. That's part of the flexibility of the whole software, is you can order it how you want. Sometimes you want to make a change later, depending on all the other changes that you need.
That's the thing. Now we have all of this. Everyone now is doing a lot of non-planar, multi-planar, not so much continuous, but control. But if you don't have the right architecture, you will find a wall very quickly of the amount of designs you can use. And we've seen it over the years doing it, that you need to have that kind of architecture and know how to develop it accordingly.
Yeah, exactly. So we have the same workflow here, but for a robot. And that's also another feature. If you have multiple hardware options in your factory, in a workshop, you can simply change the machine that you're using in the workflow, and it will recalculate for that new machine. So here, with our safety checker, we can, for example, pick up some errors based off the location of where we're printing. So in this case, we have an axis limit and a wrist singularity. And we're very confident in checking those. And it's because we're a bit close to the robot, so it's having to do some awkward positions. So we can move our meshes, but we can also move our polylines. You can see we can move them to where we need to. Here I've purposely moved it to a very awkward location for the robot to show that we can also check for reach limits, and we can visualize those very cleanly as well. So if I go here, it is pinging up with lots of different errors, as we expect. And it's just loading our reach analysis. So we've got our reach limit issues, and you can see it's highlighting the specific areas of the print that it can't reach.
Yeah.
So sometimes if you're doing very tall parts or very long parts or combination of, you need to know what it can and can't reach. And of course, here we know it's in a terrible location, but it's incredibly useful information. And then finally, we move it to somewhere very sensible. We can stop teasing the robot, and we've got a nice green shield, and we can print the part just fine.
Very nice.
Let's also shift it up a little and take a look at some concrete printing. So we've got a massive concrete gantry printer here, and we have a wonderful house that we're going to print. So this is our house, and we can slice this apart, as we always have done, nice slice operator, and get a nice clean result of the house here. But we can do a few other things. We can make it continuous as before, but we also have a special infill option for architecture called walled ribs. And that's because in architecture printing houses, we have a lot of requirements for printing kind of a continuous reinforcement, conformal reinforcement within your walls.
Mm-hmm.
And we can see that pattern here. So we have this kind of nice wavy pattern. And then, like I said, it's conformal to the geometry. So you see it follows the curves of the house. And also, it doesn't matter if it's on thinner sections, it will do it in there as well. And you can see it, a nice solid view.
Yeah.
Like so. And because we can change the position of our seams and we can automate them based on proximity and all these kinds of things, we can minimize jumping time. If you're printing houses like this, you've got different rooms and wall sections, for example, here, until they connect later on. This is an independent section. So you need to make sure that they are, your seams and jump areas are in optimized locations.
Mm-hmm.
Very nice.
Very cool.
So let's also take a look at our options for revolving. So we now actually have a new dedicated slicing mode called revolve, which I'm not using in this case because it's very new, so new that I haven't created a workflow for it yet. But we have this kind of cylindrical object here. This is essentially just a bowl. So we have this, and to slice this, it needs to actually be non-planar. Because if we sliced it horizontally, the step overs here are going to be massive, and it's not actually going to print properly. So we need the layers to be smaller here, and also it needs to be directional with the bowl itself. So we can do that using our non-planar slicing mode, and we can use some guide meshes to do that. So non-planar works with guide meshes. So depending on the geometry, you can either select surfaces or you create guide meshes in CAD. I can show you a more conventional non-planar use case later as well. So let's lock that. So the first guide is actually this cone here, and that's at the tip of the bottom here. And these meshes are being used as guides for the slice, but also the tool orientations. And then the other guide is this circle here. So this is fairly a bit more obvious as to how it's working. It's just a flat circle. So the shape of the bowl, it's flat. So the layers at the top are going to be nice and flat. And we can actually, with those, CAD options in the software, this is essentially how the non-planar slice works. It will tween these meshes as guides. Of course, much finer than this, but you can see how our layers are going to kind of gradually conform to horizontal, and they'll start smaller here. So in our slice operator, we can pick non-planar. We pick our two guide meshes. We also have non-planar infills. We can add more walls. We can do all sorts of fancy things. So you can see that our layers at the bottom are actually much smaller.
Yeah. And that's one way to do it. We still have the compensation on the full cantilever to go still horizontally if we need to close to fully print on an overhang.
Yeah, I think in that case we'd use the segmented slicing mode, and that's kind of our own version of like a geodesic type slicer. And that would be a case if you have this bowl where you needed to close it off on top as well. So it would slice much like this, and then the layers would come inwards as well, which is very fancy indeed. And then
more challenging toolpaths because physics play. Physics starts to become a reality here. But yeah.
And then here, I mentioned we can manually set our tool rotations and tool positions. So with the edit operator is where we do that. So we can set tool rotations, and we can do a number of different things here. We can set them to specific value. We can have them smooth around each other, orient it, rotate it, orient it on a mesh. Or in this case, I'm doing a revolved incline. So I know the part is cylindrically symmetrical. We can rotate it on this bed. If your print bed or external axis isn't able to do a continuous 360, which some aren't, then we can work around that. So for example, we can use a filter operator like I used before, but this time by every nth layer. So what that means is here is I'm filtering every second layer. So if I put 3, it'd be every third, 4 every fourth, and so on. And I can reverse the direction of that. So let's take a look at it now, because as it is now, it will just do a continuous revolve if you've got a print bed where it can just keep spinning around, which is a nice luxury not everyone has. So we can filter half the layers, reverse the directions. You can see they're all pointed to the right before, now they're all pointed to the left. And then once we combine those together, you can see that they are going back and forth. So the bed will spin one way and then back the other. So we can utilize or work around those hardware limitations as well. For this case, I think we're just using the classic constant 360. Turn off that travel mode, travel line, doing a dance around. So we can see the bed is just rotating underneath. The tool is almost kept fixed. It's just moving up and slightly out as the part prints. That bed is rotating. It's all nice and automatic.
Yeah.
And also, when I looked at the edit operator earlier, because this is a Fronius system, in this printer config, we will have enabled process parameters. So we can actually change our process parameters here. And if I use a new edit operator, we can see, if I just do it on anything, that we can call a different process ID. So for a Fronius controller, they're job IDs. For other technologies, it could be anything else. So we can, as long as it's something that you can call in the toolpath, we can refer to it here. So for wire arc, it's often the case that, say, on your first layer, you're using one set of welding parameters. On your following layers, you use another set of welding parameters. On weaves that connect to other weaves, the end of that weave, you need a different welding parameter. So we can isolate all these different regions, filter them out, do whatever we need to do, give them their different job IDs or welding parameters or whatever thing we need to call. And it will, in the toolpath during printing, call that and make that change. So we have another example here. This one is kind of like a repair job. So we could use a cladding operator here, but actually we use a horizontal slice just creatively. So for example, we can use cladding, select surfaces to print material onto them. In this case, in this centrifuge type geometry, we need to add extra material on this inner wall. So we can use mouse selection to select the surfaces that we need. And then we get a slice out of this. So we get this nice set of layers that we're going to use. And then I can manually set my tool rotations in this case. So the first one I'm doing is a revolve, like I did before. So if I turn on my tool rotations, we can see that our X axis is kind of following the travel.
Yeah.
And then I'm going to rotate the X 60 degrees. I'll rotate around X 60 degrees. So now this blue, which is the Z, which is in the tool, our tool is going to be slightly inclined now. And then finally, I'm also rotating the rest 90 degrees.
Yeah.
I can also add a second or as many additional walls as I need, which is what I've done here. So we're adding 2 walls of material to our centrifuge. And we can see what the effect of those tool rotations has been. So the bed will rotate, tool is kept vertical, 60-degree deposit cleanly without colliding with the robot or the part, and we've applied our first wall, and then we can move in and apply our second wall of material. So we can very cleanly repair these kind of revolve geometries as well. I showed you that automotive part for infill optimization earlier. We can do something very similar for metals as well, using different kind of printing parameters. Like we said before, we have some limited CAD ability in the software. So here I've actually used a plane to slice this, or to cut this part into 2 halves, and make them different slicing settings. So if we combine those 2 halves, you can see that we have this kind of weaving and contour combination. But due to the nature of the multipliers of the weaves that we've used, we've got a gap here, and there's also a gap here. So similar to what I've done before, I can filter these different areas, and I can actually, in this case, extract like the very end of that weave, and I can move it along and make it thicker. So if we do that for this section as well, the other weave, and combine that with the weave. And then let's take a look at the final result, I believe. Yep. You can see now that we've thickened this particular bit up. And in wire arc additive, it's not usually the case where you change parameters like dynamically based on speed and thickness, like you can with a polymer extruder very easily. Just change the RPM, sequence it, or synchronize it with the speed of the robot. Usually you're a lot more fixed to a set number of parameters in WAM. So either here we could give it a different welding parameter, or in our toolpath operator for these kinds of technologies, instead of having a dynamic extrusion where we can set different speeds for different kinds of line types, we can set a constant rate of deposition. So we know how much material we're depositing at a fixed rate. The robot or the gantry will then go at the speed that is needed to deposit the correct amount of material. So point being, we go at a constant speed for this section, and then for this thicker bit here, we move slower. And as we move slower, deposit more material. So we can fill in these kinds of gaps nicely. We can do other things as well with regards to optimizing for like stress or thermal buildup. So here, for example, we can filter by every nth layer again, reverse the direction, combine it. And what that means is your stresses as you build up, they won't be, one directional. We can kind of try and cancel them out and keep the part a bit more steady. We can also add extra material. We can compensate for slumping, things like this. There's lots of different tools and tricks and hacks in the software that you can do to really get the most out of your challenging technologies.
Yeah, very cool.
So we've seen a lot of robots. We've seen a 3-axis gantry, but we can also do 5-axis gantries. So here we have 3-axis plus 2. So in this case, we have this kind of duct geometry. And we can slice this, as normal. We've got infills, we've got outer walls, all that good stuff. We turn on our solid view. We can notice that maybe the part hasn't been designed for the process, or the parameters haven't been designed for the part, and we have kind of odd wall thicknesses relative to the file, to the geometry thickness. But here we're using a thickness optimization, and we can see from the analysis that the algorithm identifies that the outer walls are perfectly fine relative to the CAD because it's net shaped to the part. But the inner walls, the infill, they need some changing, so it will automatically change it. And now our thicknesses have been resolved, so we can actually print the part solid as we need it to. We can also see that this part has an overhang. And that might be an achievable overhang, in this case it's powder laser DED. But regardless, we're going to see a reduction in quality here because the laser isn't as concentrated, because you've got some step over, because the powder's going to miss a bit. What would be ideal is if our tool was oriented normal to that angle here. But you don't want to angle it everywhere the same, because here we might want it here, and here we want it here. So how do we do that? The answer is very easily. We can just look at our outer walls here, because we don't need to do this for the infill, because the infill's already solid. And with the edit operator, tool rotations, we can orient our tool, specifically our tool Z-axis. We can orient it towards the previous layer. So let's take a look at the before and after. So here's the before. On every vertex, we have our TCP. So this is on that slope. We can see we're horizontal, so all our tool rotations are normal to the print bed. And then after our tool orient, we can see that they are now actually guided on every point relative to the material below it. So here, they're sloped here. Here, they're sloped like that. And everywhere else where it's still horizontal, it's still horizontal. So we have them exactly where we need them. So that's a nice automated way of doing it. Because we've got lots of changes in tool rotations depending on the geometry, we can also smooth our tool rotation so it's not going to jump. So we can smooth them out, which is wonderful. Do a final optimization for any remaining overhang, changing our speeds in those areas maybe. And then finally, we can jump to our toolpath and we can get it printing.
Mm-hmm.
And we can see as we approach that sloped area, that's when the external axis really kicks in.
Yeah.
So you can see that it's all auto-oriented. In this case, the warning is for workspace limits because it's quite a big part and quite a small machine.
Mm-hmm.
But now you know the part is too large for the machine.
Very cool.
Okay. We've gone through a lot of different things, a lot of different features, different technologies, different kinematics. And there's
a lot more, you know.
Yeah, absolutely.
I think that's awesome, Danny, as a starting point for our audience. Extremely helpful to understand the plethora of work all of you guys are working on. So thank you very much. That was very useful.
You're very welcome. Always a pleasure.
Thank you, Danny.